So as we already discussed, basically the system is this one. So you have here a sphere that is trapped with an optical tweezer. Then you have bolts that you can use to drive the cavity along the axis. Okay, these are typically called output bolts. Then you have the harmonic potential, is created by this optical trap. Then you have the cavity mode that you use to couple to the center of mass and the center of mass mechanical mode, and all the rest of the electromagnetic field, which are what you call the free modes. So basically, there will be all these parts in the Hamiltonian. So let me go to, so if I can write the Hamiltonian in this way, taking into account all these terms, and I will go. So first of all, you will have the mechanical kinetic energy of the center of mass. You will have the energy of the cavity mode, the mode that you're interested in. You will have the free modes, so all the other electromagnetic modes which are living outside the cavity. And you will also have, from all of these, you usually single out the ones that are just one-dimensional and are used to drive the cavity along the cavity axis. Then you will also have the coupling between these output modes and the cavity mode. This is the typical thing that creates the damping in the mirrors. With the typical parameter gamma is assumed to be constant for a given bandwidth, and this is the typical value of kappa, the decay rate of the cavity. And then, so up to here, that's very standard cavity cooling. But now the mean part is the line matter interaction, which is the term that describes the interaction of the light field with the electric object, which is a polarizable piece of material. And the interaction is the following. So it's the energy of the field at position x interacting with the polarization field at position x, integrated over the volume of the sphere. Okay. And note that now this integral, the volume of the sphere, depends on where the sphere is, on the position of the center of mass. And this is actually at the end giving the coupling with the center of mass motion and the coupling, for example. And now, what we know is that in the field, that the particle field is not very large. So if the polarization is typically context proportional to the electric field applied. And the constant of proportionality for a single atom, we know how to obtain it. If you would have a bunch of atoms, then it would be quite difficult because you should do like a microscopic theory to know how, the polarization depends linearly with E, because there might be many self-interactions between the different dipoles inside the object. But actually, you can also look at the microscopic properties of the electric objects, and you know that there is this nice expression that the polarization is proportional to the electric field with a constant proportionality that defines the electric constant of the object. And this is the relative electric constant. Then we will always use polarization is proportional to the electric field with a value that depends on the electric constant of the sphere. So then, basically, we have all these terms which are kind of boring, these three ones, but the interesting one is interaction term, which now is equals as the integral of the square of the electric field integrated over the volume where the sphere is. And now the only thing we have to do is say, okay, so the electric field now is composed by, it has different contributions. So it has a contribution given by the cavity mode that I have to write, as Dan was writing, okay? Sorry, the free modes. Okay, so it has modes which are integrated over all, so it can have any momentum, any direction. Okay, we have free modes. There is the mode in the cavity, okay, which is this function with the typical cosines with the log, if you know. And then from some of these free modes, we identify the ones that define the tweezer, which are classical. Okay? So we just consider the tweezer part to be classical. Now I can take these three terms and put it inside and see what are the terms we make. So first one, the tweezer to the square, integrated over the volume of the sphere, will give me just a trapping potential, okay, with some given trapping frequency that will depend on all the physical parameters. The second one, the term that goes with the cavity mode to the square, integrated over the volume of the sphere, then it will give me the typical mechanical coupling at the single photon level. Okay, so and then the other ones actually are the Drossy terms. Are the free terms interacting with the cavity and the tweezer. And this will account for scattering, for light scattering. And there will be another term, which I omit here, but I will discuss later, which is the integral of the square of the free modes, which this yields interaction between the free modes due to the presence of the sphere. Okay, the fact that there is an effective interaction between the free modes due to the presence of the sphere. I will mention this later, because for when the sphere is much smaller than the optical wavelength, this term is irrelevant, but when the object is larger, that's very relevant. It makes things very interesting. I have a slide number for it. But now let's assume this is like a dipole, because it's what it is. But the sphere is much smaller than the optical wavelength. You can think as being a dipole. Okay. So then we have this Hamiltonian now. We have the typical optomechanical Hamiltonian, center of mass motion, a cavity mode, and optomechanical coupling, and we have expression for these parameters. The coupling frequency depends on the intensity and the waist of the optical tweezer, as well as depends on the dielectric constant. And this is typically can have hundreds of kilohertz per air. And the single photon coupling now scales also with the volume of the sphere. There is also spherical volume here. There is the length of the cavity, the waist of the laser beam, the cavity, and the dielectric constant. And so basically, the cavity would increase if the sphere would overlap with a larger cross-section of the laser waist. The larger the sphere compared to the waist, the higher the coupling will be. But of course, the higher the coupling. Okay. And then from the optomechanical, then there is the other part, which is just the coupling with the output modes. Okay. So the modes that you use to drive the cavity. So how to couple to the cavity mode. And the scattering terms. Okay. The terms that describe the coupling of the sphere and the cavity mode to external free modes. Okay, so we have now the Hamiltonian. So this is describes the physics of the principle of everything. Yeah.
It starts with all the tracing macro. This was A naught.
Yeah, A naught is just two different. So A naught is the mode that describes the ones that are along the line of the cavity, the ones that you use to drive. It's where you will send the laser. And A is the node of is the mode of the cavity.
And B is mechanical mode.
And the mechanical mode is B. And the free modes are going to be these A case. And now the nice thing is that I have this Hamiltonian, so I can derive the master equation because that's a total Hamiltonian. And for instance, what I can do is the following. So I say, well, I'm only interested in the optomechanical coupling, so I can say, what about if I want to describe the state of the joint cavity mode A and the mechanical form B? What I have to do is trace out the free and the output modes. Okay, so I trace out all the other modes, and I will obtain an equation that describes the density matrix that accounts for the motion and the cavity mode. Actually, you can do this carefully, and then what you obtain is the following. So you take a master equation in which you have the Hamiltonian, the optomechanical Hamiltonian that we want, plus some dissipative terms. And actually, the dissipative terms, first of all, you have two of them that account for photon losses. And there is this term, you see, whenever you have a master equation of this type, with this limbulant term, there is a trick, which is you look at the first operator here, and this is telling you the process. Okay, so the first one. This is an A, it needs to be decays, so you lose photons. If this would be a data, it would be heat. Okay, so these are both photon losses. And what goes with kappa, meaning it's a decay rate due to the mirrors, to the fact that you can couple to the output modes and lose the photon through the mirror, typical one in cavity quiving. Plus an additional one, that is that you can also lose photons because the cavity photon, the photon that is in the cavity, can scatter with the sphere and go away. And this also provides photon losses. And the second one is that actually these scattering events also produce some recoil kick into the sphere, and this creates diffusion, okay? Like in ions, like what Peter was describing. It's exactly the same. It's this diffusion here. See that now the jump operator here would be x, meaning that you measure x. You will either cool the motion, another excite. You either cool the motion, another you have these parameters, which actually you can obtain, and you can have this kind of constant for the decay rate. So if I plot now the decay rate due to light scattering, the fact that you lose the photons due to scattering with the sphere, in units of the decay rate of the mirror, which you assume is fixed, of course, depending on the size of the object. And you see that as soon as you have objects that are comparable to the optical wavelength, actually the decay rate due to this starts to dominate. It means that the finesse of your cavity will decrease a lot due to the presence of the object. But if the object is much smaller, it's of the order of tens of nanometers, then basically the finesse should be the same in principle. And also another condition that we will require in order to do ground state cooling is that, for instance, the light scattering diffusion is smaller than the cooling rate that we will have. Okay, so that's why it doesn't mean that. So here I should not talk about Qs, but of course I have to take into account that light scattering can create some heating in this sense. Therefore, this has to be smaller than the cooling rate. Otherwise, it will not go to the ground state. And just to show you, these are expressions you can obtain. Because the cavity decay rate due to light scattering goes with the volume, so with the power of r to the 6, basically related to the Rayleigh scattering. It always goes with r to the 6. And also then the light scattering, so the photon recoil heating, or the diffusion rate, goes with the volume. Okay. And this depends, this is the contribution due to the cavity, but also the contribution due to the tweezers, because also the light from the tweezers also scatters off and produces some heating. And therefore, this is something you can account for, take into account with your calculation. But the message is that provided you have objects which are at max 100 nanometers size, and you work in time scales 1/gamma scattering, okay, then you can say that the center of mass at room temperature is effectively isolated from the environment. Okay. So I think it's to show the advantage of maybe trying to be in a scenario similar to ions in the fact of the discussion we had in the lecture of Peter and somebody asked why they can cool so well with ions compared to mechanical oscillators. Here, in principle, if you would use very small spheres, then you would be at the similar scenario. That's correct. Yeah.
What sort of time scales are we discussing?
Yeah, this I will discuss, but this depends on the. Yeah, but typically it's much smaller than the cooling rate. Yeah. But they grow with the volume and have to be reckoned. But they range over typical milliseconds. Okay, so what about other sources of decoherence? So one could say, well, you say you don't have a thermal bath because you levitated, but of course the center of mass, there are many other modes inside the object, right? There is not only the center of mass. Actually, this is something we considered carefully, and we took the opportunity to kind of derive theory, or to an extent, something that are very well known. For instance, we made this quantum elasticity, which was to perform a canonical quantization of the deformation field. You have an object which is elastic. There will be many forms around, and you can just quantize it carefully. And then you can obtain a Hamiltonian of this time, where you have the Hamiltonian that we had before, plus an additional term. One that contains all the internal modes, all the internal phononic modes that there can be in the sphere, plus an interaction term. An interaction term is basically an interaction between all these modes, all these internal modes with the cavity field, plus the interaction of these internal modes with the center of mass mode. And therefore you would say, well, then I have here a thermal bath, right? Because now my center of mass mode is coupled to all the internal modes, which are going to be hot because that's the bulk temperature.
Is this what leads to the Q of that mode mostly?
Yeah, I mean this could provide a Q.
Right.
I don't know if this provides a Q, but it's actually very small because of the following reason. Okay. But just to say that these things can be calculated, and the point is that this is very small because when you look at the frequency of these internal modes, since it's given by basically the R modulus divided by x, the square root, and divided by R. Or more intuitively, is the speed of sound divided by the size of the object. That gives you the typical frequency. And since you are using nanometer objects, these frequencies are huge, are 10 to the 11 hertz. And that's very good because the center of mass mode is typically megahertz at max, so there are 5 orders of magnitude difference, so they are completely off resonance. Therefore, the center of mass does not couple with internal. Nevertheless, what we always wanted and always had in mind is that, of course, this number is very appealing. So the question is how we use these internal modes to do optomechanics, because here we also have a coupling. But of course, that's not so easy because this coupling is also very small. So, but something we always had in mind whether there will be a clever way to address these huge frequency modes in these small objects. So therefore, you just technically can make an adiabatic elimination of all these three modes, and you see that it does not anything. It doesn't provide any effect to the dynamics. Okay. So I would like to mention now other possible, make a summary of source of decoherence. So as I said, well, clumping losses we don't have because it's levitating, and therefore there are no clumping losses given at room temperature. That's of course a nice thing. The coupling to other internal modes is negligible due to the fact that these internal modes have huge frequencies. Of course, you should always take into account this position localization decommitted due to air molecules. But as I shown before already in the analysis, these are only start to be relevant when superposition sizes are very large. But if you really want to do optomechanics, you are in such a small wave functions that this will not be relevant. An important thing might be black body radiation. Because the fact that we don't have clamping losses, that we don't have thermal contact, it means that all the heat that the particle absorbs, it's very difficult to be released because we don't have the thermal contact. Right? So the only way to release it is through black body radiation. And black body radiation is quite a slow process, so the overall effect is that the object heats up, and it will actually always be at much higher temperatures of the room temperature, most probably. Okay, and therefore, I mean, we would like to use objects as much transparent as possible, but the question is, I guess, in experiments, whether for instance, the properties, the transparency properties of bulk silica are the same when you are using a 50 nanometer speed, whether these properties change. That's something, I guess, that at some point might be relevant. For sure, for these large superposition ideas, okay, somehow, I guess, it's a lot the potential of doing very, very large ones. And as I said, a very important one, the dominant by far, should be scattering. But we know how to treat it and estimate it, and this actually puts a bound to the size of the object, saying that we should really use very small objects, otherwise we will scatter so many photons that will create a lot of diffusion and a lot of heat. But of course, these ones are things that we can somehow analyze from a theoretical point of view. There are other things that might be more difficult to analyze in a more rigorous way, and probably depend on the particular experiment. Something like that you have to be sure that there are no charges, or if there are, that they don't couple to other things that might provide decoherence. Laser fluctuations, as always, have to be very well stabilized. Things like anisotropies or effect of axial motion, this can be accounted. Typically, it can be accounted for, and typically it seems that it can be controlled. But of course, I want to put the question mark, because you know that many people are trying to do these experiments, and they are finding that they decrease the pressure, and at some point the beat is lost. Okay, so.
I'm sorry, I have a quick question. Laser fluctuations is something that we have pretty much under control. Do you have any kind of estimate?
Yeah. So I made the estimate in the very beginning, and it was clear that it was not very problematic.
Okay. You need a Chen-Hall laser? Or?
Yeah, but yes, but somehow, at some point I wanted just to be specific on the most, maybe more interesting from the theoretical point of view. Yeah. But of course, there are experiments being done nowadays that we know that they lose the beat at low pressures, and of course maybe that we forgot something, or that there is something that is. But at the end, somehow the physics are kind of limited, right? For the electric object, like it's like the cavity with a single atom, but with an atmosphere. So there shouldn't be so many possibilities for think that none of the experiments that I'm aware have done a very good 3D feedback cooling of the sphere and then go to low pressures. There was an experiment by Nawalny from ITAMP that they did. They actually decreased the pressure, but at some point the peak was also lost. So we need a very good feedback cooling, but of course it would be nice to understand why is this happening as well, just to progress with the experiments. And I think that's a very good point to stop this lecture, so I thank you very much for your attention.